Oh, good. Okay. Sorry. Hello. Hello. Okay. Wait. First of all, I'm sorry. I don't have them. I don't have them. I'm just saying that. That's all well, it's not all I'm saying, but I don't have them yet. I am sorry. Um, but hi. Okay. Hi, John Ford. Hi, Maisha. Hi, hi, John. Hi, Leslie. Hi, Michaela. Good afternoon, Jalen. Hello, Alona. Good afternoon, Zimin. Good afternoon, Andrew. Good afternoon, Weishi. Good afternoon, Manoj. Good afternoon, Mark. Good afternoon, Ruby. Good afternoon, Athia. Good afternoon, Eric. Good afternoon, Jessica. Oh, I won't even respond to that. Okay. Good afternoon, Nick. And sorry about the other day. I hope you okay. And good afternoon, me. I'm saying again, I don't have your exams. I'm just going to keep saying that, maybe so that it comes out of my mouth instead of yours. I feel terrible. You will get them. I don't know what else to say at the moment. I am working on them and scrambling to catch up. I'm just saying I don't have them. Good afternoon. That is funny. Okay, that is funny. I think, I hope, about the Denny's. Moons over my hammy. Good afternoon, Lizzie. Hi. She's first to fight me? Oh no, she's first. Okay. Catch me. I don't even know. Oh my God, I don't even know what that means, but I'm scared. Okay, wait, I'm letting other people in. And if I'm not careful, no, I am guilty enough that if I'm not careful, I could make, believe me, what you want is for my guilt over these exams to ultimately just dribble its way into more compassion in your grading. And that is what will happen. Oh, wait. Oh, okay. So, okay. I'm sorry to hear that. Okay. Sorry. Okay. Oh, yeah. All right. I'm getting scared. Okay. Like, no, and in this class, I'm particularly scared of my, because I feel guilty enough that if I'm not careful, I'm just going to I'm going to turn the whole class into like a bunch of apologies or jokes about that. And I don't want to do that because that's actually just like making your life worse. So, oh my God. Okay, I'm not even trying to say, right. So but you will get them, and you will get, and you will get, due compassion and understanding in your grades and all that stuff. But I'm going to just move on now, because again, like if I'm not careful, I can make the situation worse by talking about it all, period. So yeah, but I will tell you this, I'm going to try to, I'm going to, well, anyway, no, I'm not even going to say it. All right. What I want to do today, though, is continue the new material that the last bit of material that we're doing at the end. And I want to let you know also, in other words, not that. In other words, okay, yes, I want to do the, oh, now I'm scared. Okay. Yeah, Denny's versus that. Yeah, that's a tough call. Moons over my hammy versus silver dollar pancakes. Tough call, definitely. What I want to do. Oh, and good afternoon, Starnisha. Yes, and hello, anybody else I missed. I'm sorry. I'm a little something. And by the way, for whatever it's worth, too. I hope you noticed, and I noticed, like if you're here at all today. By the way, great praise be unto you. And I really do want to make it worth it to you in a very physics sense today, as entertaining as I do find this class. I want to make your time here worth it because believe me, I know the day before Thanksgiving in the afternoon, showing up at all anywhere, like basically I've always been sort of outraged and freaked out that John Jay even holds classes. And it actually, believe me, it's super inconvenient for me to be teaching the night before Thanksgiving. And I know it's super inconvenient for you guys. So if you're here at all, first of all, praise be unto you. Second of all, I hope you noticed the thing in the Google Classroom where you're basically getting 14 points just for the fact that you acknowledged showing up today. Also, it's a little unusual because we also had class last week, but I do feel like I owe you this instruction time. So I want to make it worth it. Like maybe it won't be fun, but I want to make it substantive today. And what I mean by that is I want to get back to this material that we're using to sort of close out the semester. And specifically, I want to try to explain this material of Newton's laws in a way that will help you with the lab that you were just having, or some of you were with the whatever lab questions you have on this board meeting that you had about force diagrams. And so I want to directly address that today. Oh no. Oh, well, I thought that'd be a good thing, but I want to try to help with that if things are still outstanding. And then also, I don't know if in this class, if God forbid, you're also doing lab 5, and if you have a formal, in fact, you do. Oh, good. Oh, funny. Okay. In fact, I'm going to ask directly right now because the two different Physics 203 sections are in slightly different places with labs. So let me ask you: do you have any awareness or knowledge of a lab 5, which is called slow down? Has lab 5 even been begun, or do you have any awareness of a formal report like ever being due in lab 5 for you? Like even if not now, by the end? No. Okay, not yet. Okay, fine. So you're in lab 4 right now. I mean, correct? Or you're 4. Okay. And is it true that the formal or the whatever is due for 4 has not been turned in yet? Is that correct? Like, and I totally appreciate these answers, and you're all getting points. Yes, it's not been turned in yet. Okay. So then for whatever it's due Monday. Okay. So hopefully, today, what I'm going to do will hopefully be helpful to that. And maybe even hopefully might even reduce some, if there's any kind of inter-lab group, like maybe this will be easier for the groups to work together as well if I give you some information about this, because I know it's that time of year where working with others gets harder for sure. I know that working with others is like a big, hard, annoying part of physics. And I know it's particularly hard, like in COVID. So in any case, for good or for bad, what I want to address is forces, and particularly like the hows and the whys and the hows of force diagrams today. Okay, that's hilarious, Nick. Oh God, now I'm seeing, okay. I don't even, where did the cranberry? Oh my God. Okay. Oh, I get it. Thanksgiving. Right. We should all meet to have Thanksgiving at Denny's. That would be, okay. Physics with a side of gravy. Oh my God. Okay. That is funny. See, this is what I worry about. Okay. Did you say that I had ADHD? All right. So. All right. Okay. I'm totally going to ignore this chat now. You guys are very funny. Okay. So it's on site. Oh my God. Okay. Like really, it's so unfair. If you guys were all one big kickball team, you would like not pick me, and then you would, and you'd put me in right center field. Okay. Oh my God. Okay. All right. So here's what we're here to discuss, or I'm here to discuss Newton's laws. We started them 2 days ago. I want to try to make it clear what role the diagrams play in problem solving. Like the ultimate point of physics, of course, is to solve problems that are quantitative, i.e. mathematical in nature. Newton's laws may look at first as though they don't help you solve problems. Particularly the diagrams may look like they don't have anything to do with solving problems. I want to show you today how I am ignoring this, how the laws and the diagrams come together to solve problems. All All right, so the first page. So this says how to use Newton's laws in order to solve problems in and out of the lab. Now, remember, yesterday you wrote down, I'm sorry, Monday, you wrote down Newton's first law, and I quickly started talking about it. Then I want to be clear, I stopped in this class at the end of saying anything about Newton's first law, but then you might have noticed if you pulled the PDF of class notes from Google Classroom, that in the notes, I also wrote down Newton's second law and Newton's third law, and I'm sure you've heard Newton's second law of motion and Newton's third law of motion before in like 6th grade or whatever. I'm going to repeat them again today. But I imagine that the actual words of those laws will not be a major surprise to most of you. What I'm here to do is to try to put those laws in context, tell you really what the purpose of them is and how to use them. So the first law you already wrote down. The first law, right, is unless acted on by a net external force, an object in motion stays in motion, and an object at rest stays at rest, and an object in motion stays in motion at the same speed in the same direction. That's what the law says. Now, what's the point of that? Like, what does it do for us? Well, what it says here is, I'll just read out loud. Newton's first law tells us what would or will naturally occur with a mass by itself. Newton's first law is the answer to the question, how would an isolated mass tend to move naturally? And the answer is that an isolated mass would not spontaneously change its velocity. Like the first law is really divided into two cases. It says what would happen with an object at rest, and then it says what would happen with an object not at rest. Now, there's a reason that the law addresses two different cases, even though what the law is saying is ultimately the same about both of those cases. The reason the law divides its attention into two cases is why the law says, like, an object at rest will stay at rest, and an object in motion will stay in motion at exactly the same speed in exactly the same direction. Like, it's going through pains to say that no matter whether you're at rest or you're not at rest, what you will naturally do if you are an isolated object is you will maintain constant velocity. That's what the law is trying to say, right? It's saying no matter whether you're at rest or not at rest, what you would tend to do, if not influenced by any other object, is you would not change your velocity. No matter what the law is saying is objects naturally maintain constant velocity. That's what the law is saying. But the reason it bothers to say it about two different cases is because it knows, because Newton knew, Galileo knew, that we all actually tacitly agree with this law when it comes to one case, and we all don't tend to agree with this law we all don't tend to find this law like obvious or reasonable in the other case. Like, we all expect that objects sitting still will continue to sit still if nothing is done to them. Like, I'm looking at my can of Coke on the table. I walk into the room, I see the can of Coke on the table. I expect that it will not spontaneously start moving to the left. It will not spontaneously start gaining speed. It'll, right? But so we don't really need to be told that, we would think. But when objects are moving, we have a tendency to expect, to think that objects that are moving will, of their own accord, spontaneously start slowing down and coming to rest. We have a tendency to think that for something to be in motion, an explanation is required. We tend to think that nothing needs to explain why something's sitting still, and that if it is sitting still, it's going to keep sitting still. We tend to expect that doesn't require any explanation. I mean, we tend to think that. But if someone tells us about something that's moving, we tend to think, oh, well, that requires an explanation. Like in those diagrams you were doing in lab 4, like if you were doing a free body diagram of a cannon that was shot out of a cannonball, right? And so the cannon is like up here in the air, and it's like right now at a certain moment, like flying up and like to the right, at some speed and some angle, and you're asked to draw a diagram of it. Right. And I want to, I mean, I think it's worth, I think it's all worth us all talking about this. There's a reason, like, yeah, right. So if someone presents you and someone says, hey, there's a cannon over there, look at that cannon that's like in flight right now, on its way up, draw a diagram of it, analyze it, make predictions about it, or like compute its acceleration. There's a big tendency in all of us to think, well, if the thing is in motion, that requires some kind of explanation or something. So if someone's asking me to draw a diagram of something that's in motion, and by the way, not just in motion, but like in motion up and like at some high speed, right? This cannonball is like, it's not just like falling, it's like going up, right? So we tend to think, and by the way, also same point about the bucket or whatever, I can't remember what it was, like the sponge or something that was like sliding across the desk, that we just like, when we walked into the room and happened to see something sliding across the desk, maybe it was initially pushed, we don't know, but like right now it's not. Oh, the milk carton, thank you. Yeah, thank you very much. Yeah, the milk carton, right? There's a strong tendency among all of us, even at deep stages of physics experience, but especially at early stages, there's a deep tendency for us to think, well, if I'm asked to like analyze a cannonball that's already in upward pointing flight, if I'm asked to like draw a diagram of it and like start thinking about it, like, don't I somehow have to like add an arrow or something, like some kind of velocity arrow or some kind of force arrow from like the cannon itself or something to explain the fact that this thing is moving? Like if it's moving, but mustn't there be a force on it or something, that then therefore shouldn't I draw an arrow if it's a free body diagram, or shouldn't I draw another circle like with a line if this is a system schema or something like that? Everybody has that tendency that to think motion needs to be explained, that things sitting still doesn't have to be explained, but motion has to be explained. We have a tendency to think, even when we're not consciously thinking this, we have a tendency to think, oh, for there to be motion, there must be a force. What this law is saying is, no, 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 au contraire, mon frère. I know we think that, therefore this law, and again, this is not the wording of the law. The wording of the law I gave you yesterday, right, on Monday, but this is like something I'm saying about the law. The wording of the, wait, I'm just looking. This looks like a natural physics thing, so I'm looking. Right, right. So what John Ford just put, and thank you, Maisha, for like totally keeping me on track here with the correct references. But yes, what John Ford just said, if the cannonball is not acted upon by any other motion, I'll even say if it's not acted upon by any other force, I'll say it will just continue to move into outer space and through the universe in that path. That's fine. That's fine. Yes, that's right. And that's really important. Like what the first law is saying, the first law is meant to be in part a surprise. The first law is telling, the first law, honestly, it's a tribute to Galileo, but it's also kind of like a rejection of Aristotle. It's very explicitly trying to tell us something new. It's saying, you know how objects that are at rest stay at rest? You know how like we all are comfortable with that? Like, because we are like, you know how we all assume that if something's at rest, it's going to stay that way. And if you want it not to be that way, you're going to have to do something to it. You're going to have to push or pull it or something. You know how we all think that? The first law is saying, well, actually, an object that's already moving, the truth is, same reality applies. You think that you might think that an object already at moving would be tending toward slowing down, and that an object in motion will eventually come to rest. You might think that, but what we're saying, what Newton is saying is, no, not an isolated object, not an object that's by itself, not an object that is not being influenced by a force from any other object. No, you're used to seeing a lot of objects in the world that are interacting with other objects. Like you're used to seeing things sliding along roads where the road is touching the object and the road is really rough and exerts a lot of friction on the object or something, for example. You're used to seeing objects that are interacting with other objects. So a lot of the times the objects you're looking at are being subjected to forces from other objects and therefore being decelerated, being accelerated negatively, having their velocity change and slow down. We see that a lot. So we start building up an idea in our mind. But the truth is, what this law is saying is, whatever we ever believed about zero velocity, that a zero velocity isolated object will remain a zero velocity isolated object? The truth is that if an isolated object has some other velocity, the same thing is going to happen. It's also going to just maintain its velocity. And why? Why would we say, in other words, John Ford's point, that if we shoot it up, if you take an air hockey puck and you fling it down the air hockey table, right? If it's a good air hockey table where that puck really isn't touching the table, where it's on a nice cushion of air, which is like practically thin space, right? And it's a smooth puck on a smooth cushion of air. The truth is that puck keeps going and going and going until it crashes into something, or until a stick hits it, or until it hits some part of the air hockey table that's broken and doesn't have a cushion of air, and then it starts rubbing against the table or something. But the truth is, you don't even, in other words, again, I'm agreeing with John Ford's point, but I'm trying to say the thing about John Ford's point, it's correct. But he talked about the thing going into outer space. And for a lot of us, the minute I say outer space, then of course, for a lot of us, we think, oh, okay, outer space, whatever. Yeah, that's some ideal, that's abstract and has nothing to do with the real world. When are we ever in outer space? I'm saying yes, outer space is totally a right example of where objects are isolated from each other and aren't being subjected to a lot of interactions and forces. But we can create those situations, and we experience those situations even here on Earth, such as an air hockey table. And what I'm trying to say is, what Newton is trying to say is, anything you believe about the zero velocity case, you should also believe about the non-zero velocity case. That is, in general, what objects do when they're left alone is they don't not move. What they do is they don't accelerate. Objects left alone don't move at necessarily any particular speed, and they don't necessarily sit at zero speed. What they do is they maintain constant velocity. What we're ultimately saying, and I'm going to look at chat because it looks like the chat is full of physics. I'm going to look at that in 1 second. What I'm really trying to drive home, and I will flip the page and get to the diagrams and everything in a minute, but this is a really deep physics point. I mean, it's just another way of saying something we've been saying all semester, but it is the nub of physics, really, is that the zero velocity case isn't special. Zero velocity isn't special because there is no real such thing as zero velocity. Nothing is actually sitting still, nor is anything actually going 100 miles an hour. Velocity is in the eye of the beholder. Velocity is not a property that one object has. Velocity is a relationship that one object bears to another object. So in other words, an object can look like it's at zero to me because it's zero to me, because I'm sitting still relative to that object. That just means I'm moving at the same velocity as that object. Any object that looks still to me right now is on the Earth. It's not going to look still if you look at it from the sun. And both the sun and the Earth are correct. They're both valid reference frames. So in other words, last thing, and I'm going to look at the chat. As long as in other words, forces don't cause motion. Forces cause acceleration. Or put another way, motion does not require an explanation or a force. You don't need a force to be moving. You need a force to change the way you're moving. That's why we don't ever feel velocity. We feel acceleration. In the airplane, we feel it when it takes off, when it's coming in for a landing, when it turns, when it bumps. We don't feel it when it's cruising, because velocity is just a relation. It is not a thing. Now, let me just look in the chat. So that's what the first law is really trying to say. Sorry. So the first law is trying to say, in the absence of forces, if in the absence of other objects interacting with us, what we will do is not accelerate. I don't know what our velocity will be. It could be 0. It could be 100 miles an hour. It could be 10. Whatever, our velocity could be whatever. But if other objects don't interact with us, then what we do is we maintain an acceleration of 0. So the first law is the base case, like the control, what happens when nothing's happening. And then the next two laws tell us how the reverse. They say the next two laws that we're now going to get to tell us what happens when there are net external forces acting on an object. And the answer is then the object will accelerate. And the next two laws tell us how to make that mathematical prediction. Let me just look in the chat. Hold on a second. Sorry. And maybe these are both. Oh, maybe these are jokes, which are funny, but Wait, wait. Okay, so I'm looking, I know there's jokes and physics here, so I'm going to try to do it. So first of all, there is a private message, a direct message that actually, I'm not going to read the name because it's direct, but very valid point in the direct chat says, so gravity would be the external force that changes the object's motion. Yes, that's awesome. That's awesome. And you should get points for that. Yes, in the case, for example, of the cannon ball that was fired out of the cannon, like for Monday, for the thing that you guys are talking about in lab 4 and stuff, if you're looking at a cannonball at some moment in its flight as it came out of a cannon, at any moment in that flight, the only external force acting on that cannonball is gravity from the earth. Yes, the only force acting on the cannonball is gravity from the earth. So hence, no matter whether the cannonball is moving up, straight up, or if the cannonball is moving up and to the side, like, as part of an arc, or whether the cannonball is moving down, it doesn't matter how the cannonball is moving. At that moment, if nothing is touching it, then the only thing pulling on it is planet Earth. And therefore, so the only pull on it is straight down. Therefore, that cannonball is in free fall. Like, free fall means when the only influence on you is gravity. That cannonball is in free fall, and the only force on it is pulling down, which means even though it might be velocitizing up and to the right, it is accelerating straight down. I mean, so that's right, to the direct chat person. Great question. Okay. And then John Jay had one. Oh, yeah. I bet John Jay had, I'm sure. I love air hockey, but sometimes it would hurt my, yes, I'm sure it would, John Ford. I want to go to outer space. Yes. Well, don't you feel like you're already in outer space in this class? Okay, we have a space force. Okay. Physics equals fake confirmed. That I don't even, okay. But yes. Wait. Oh. Yeah. Althea. Right. Like things naturally keep going. That's why we need brakes in cars. That's right. Things naturally keep going. The reason we need like gas and an accelerator and stuff is ultimately because of friction from the road. But round rubber tires severely do a great job of reducing friction from the road. So yes, the answer is yeah. Things, if we're not, yeah, things left to their, if something is left to its own device, what it will do is maintain constant velocity. People think that things left alone will sit still. No, people think things left alone should have zero velocity. What we're saying here is no. Things left alone will have zero acceleration. And by the way, this is why I'm saying this law, this first law, this is just the fifth, literally, this is form number 5 of Galileo's principle of relativity. This is just another way, and it's not plagiarism. Like Newton knew exactly what he was doing. He's picking up where Galileo left off. This is just another way of saying zero velocity is not special, because zero velocity doesn't absolutely exist. Like, okay, so good. All right, so the first law is like what happens if there aren't forces. So then we have the next 2 laws to tell us what happens when there are forces. So we go to the next law. Okay. Now, first of all, let me add a page, 1 second. Okay. Okay. So again, I wrote this in the notes from 2 days ago, but we didn't talk about it. And of course, you've seen this a million times and you've seen it on t-shirts and stuff, but let me say some things about it. Like, this is where the action is. F net equals ma. This is a central law of physics. From here on in, everything in physics, in a way, almost no matter how modern you get, in a way, almost every context, certainly of what we call mechanics, boils down to, starts from and comes back to this law. It's super simple in a way, but it's as a result. I mean, this is the way physics usually is. Physics is usually like about what is simple, not necessarily easy. This law is incredibly powerful. The number of things we do with it, even though it's, or because it's so simple, is somewhat astounding. And the math that we do to solve problems usually starts with us writing down this law and then expanding. Like any math, any problems that we have to solve from here on into the end of the course, any problems that we have to solve will be problems where you take a mass and you have to solve for the acceleration so that you can go back in and plug the acceleration into all the stuff that we've spent all semester developing. Like, so the bulk of the semester, what we've been saying is, you know what, velocity is just a relation between two properties. Velocity is not something that an object feels or is objectively true about the object. Velocity is not where the action is. It's changes in velocity that allow us really to predict what's going to happen to where an object is in the future. And so we have all these equations from the beginning of the semester, or from most of the semester, about where an object will be at a certain time, assuming we know its acceleration. So we've been saying all these things, assuming we know a value for acceleration. Now we're finally stopping and saying, well, where do we get this value of acceleration from? How do we know the rate at which an object instantaneously accelerates? And the answer turns out to be, well, look at all the forces acting on it. Forces produce acceleration. The sum of all of the forces acting on a given mass at a given point, well, let me say it again. The sum of all of the forces acting on a given point of mass at a given point in time, at a given point in space, is what tells us the acceleration of that mass at that point in time, at that point in space. If you know everything that's pushing or pulling on something, then you'll know the rate at which that something is changing its velocity. So the sigma, the big sigma symbol, means sum of. Sometimes people write this, sometimes people write it as, I mean, interchangeably, you could say F net equals ma, same thing. Sum of net means the same thing. It means you add up all of the forces acting on an object. Together, they will, yeah, that is a good question. And in fact, sorry. Right. I mean, yes, I've actually heard that. I do like that question. That's called my first marriage. No, I didn't say that. I think implosion is probably the right answer to that. Yes, when an immovable object. I actually weirdly have more to say on that, but yes. And when a tree falls in the forest and no one's there to hear it, when a joke is told in the forest, no one's there to hear it. Is it funny? What I'm saying here is that all the forces acting on an object produce the acceleration of that object. But we take into account minus signs. So the arrows over the F and the A, the arrows over the F and the A, I mean, the F stands for force, the M stands for mass, the A stands for acceleration. But the arrows are there to explicate that we're talking about vector quantities here. that force, just like acceleration, is something that acts in a particular direction and can act in more than one dimension at once. Like you can, just like you can accelerate to the southwest, you can push something to the southwest. So what the arrows really mean, if you look down here in the bottom right corner of the page, what the arrows, the vector symbols really mean is that F net equals ma, Newton's second law, is really part of the reason that, I mean, it looks super simple, and it is super simple in a way, but part of the reason it's so powerful and tells us so much is that really it is a set of simultaneous equations. F net equals ma vector-wise really means that at any given moment, at any given point in time, in any given point in space, if you take all of the forces acting along the x-axis on some object, then if you add up all the forces pushing to the east and subtract from them all the forces acting to the west, and I don't technically really mean subtract, what I really mean is if you take all the forces acting to the east and add to them all the forces acting to the west, but recognize that if they're going to the west, then they have to get a minus sign on them, right? So if you add up all the forces going in one direction along a given axis and subtract from them all the forces going in the opposite direction on that same axis, then you will compute the acceleration of that object along that axis. The sum of all the x forces, taking into account minus signs, equals mass times the acceleration in the x-axis. Independently, but simultaneously, add up all the forces going in the y-axis, like all the forces going to the pushing to the north, minus from them, subtract from them all the force magnitudes pushing to the south, and what you'll have is the acceleration of the object along that axis. Take the two component answers that you just got, Pythagorize them together, treat them as two legs of a right triangle, and the hypotenuse will be the overall acceleration of the object. So F net equals ma says, okay, well, so the first law says if there's no forces if there's no net force, if there's really, okay, so to Althea's thing, like the first law is saying if there's no net external force on an object, then the object won't accelerate. It's really saying if the sum of all forces on an object is 0, then the object won't accelerate. This is what the first law is saying. So, or to put more mathematically now in the second, oh, totally. And let me just, yes. But just to quickly wrap up the Althea thing and the this thing, and then the John Ford thing, and then the I will stutter more thing. What I'm just trying to say right now is we're not saying that force equals mass times acceleration. We're saying net force, sum of all forces, equals mass times acceleration. So we are actually saying if I'm sitting here and you're pushing me really hard, you're pushing me with 100 newtons of force to the north, but at the same time something else is pushing me with 100 newtons of force to the south. So this is like the unmovable post immovable object thing of Althea's. Like if something is pushing me really hard to the north, but at the same time, something else is pushing me really hard with the same number of newtons of force to the south, then we're going to have 100 minus 100 equals 0. I won't accelerate at all along that axis. That's what this is. But if there is anything left over, if there's a net force to the north, then we plug in the numbers and we can use that to compute my acceleration to the north, which I think is what John Ford is asking. Yeah, and so we could use force to find. Well, we're assuming so John Ford's thing says so we could use force to find acceleration, then find mass. What this is all about, and I will try to turn the page and move on in a second. What this is all about is that we use forces to find out acceleration. We generally assume that we know the mass, then we assume generally that the mass is a given object of interest in a situation. And then what we need is to know all the forces acting on that object in order to compute its acceleration. And then once we have its acceleration, we plug that back into all the equations that we were developing for the rest of the semester. So in a way, all of this is kind of going backwards, and you're going to see as I turn the page, it's even more going backwards. Really, we're examining the world by zooming in, we're seeing effects, like the effect of acceleration, and saying to ourselves, oh, we can develop these equations and these relations to use acceleration to predict velocity and use velocity to predict where an object will be at a certain moment in time. But then we're zooming out and going, but where did that acceleration come from? Oh, it came from forces. Oh, if we know all the forces acting on an object, then we'll know the acceleration. Then we can predict the velocity and we can predict where it is. So the second law says use forces to predict acceleration. What the second law is really saying is if you knew all the forces to list on the left side of F net equals ma, you would add them all up and you would plug them all in, divide by m, and you would have the acceleration from the right side. The question, so that's what I'm saying, the John Ford's thing. The question though becomes, well, how do I know like what's a force acting on an object and what isn't? How do I know what? And this really is the nub of the gist. Like the math is easy. Once you know what to plug into the left side, then it's just like arithmetic or maybe some algebra rearranging. But the issue for most people is how do we know what, if we're given a certain situation and asked to predict acceleration, how do we know what to count as a force and what not? How do we know what to plug into the left side and what not? That's where the third law and the diagrams come into play. So, so this just says, I'm just going to read this. I mean, I just said this. This page just says Newton's second law is the mathematically predictive law. It tells us what happens to a mass once it is subject to any number of external forces. And what are external forces? They are influences from other objects. The first law says what will happen to an object when it's just by itself, isolated, unaffected by other objects. The second law says once other objects start exerting forces on an object, then we get acceleration. So you, and this is in the notes. I'm going to turn the page. I mean, if you want me to stay on this, I will, but I'm going to turn the page, but you can tell me to turn back if you want. Oh, well, here. So now, so the question is like, really, what is a force? How do we know what a force is and what it isn't? Well, I wrote this in the other notes, but I'm going to write it explicitly right now. Oddly, to actually know what a force is or to really understand it and to know when to put it in the diagrams and when not, what we have to turn to is Newton's third law. It all seems kind of like it's going backwards because it's kind of like answer to a question, but then that answer prompts a question. So then we go back and answer that, and then we go back. So the third law is this. Again, this is in the notes from Monday, but I'm just going to write it down anyway. Okay. Each one of these laws, in a way, has a certain part that's like super obvious, so obvious that you would have a hard time rejecting it, and then has a certain part that's kind of like the surprise or the new sort of push forward piece of information, and that includes this one. Now, this law, and again, I'm trying to, I know we, oh, okay. And again, let me apologize, by the way, this is one of those, we actually are having this class 2 weeks in a row again, because I care about you so much and I miss you so much, but please just remember that technically I'm also teaching another class right now as we speak, and they like a double period. I mean, I'm not, but they will come in at 4:30. So just to forgive me, like as soon as this is over, I will have to shut down the Zoom and reopen it to the other class. Just a reminder that I can't actually hang out right after this. But anyway, and then happy Thanksgiving in advance. And again, I totally commend you for being here at all on the night before Thanksgiving. But okay, so the third law, which again, I know you've heard your whole life in some, I mean, you probably heard it in 6th grade. It's referenced in book. Well, that's interesting. That I see the direct chat thing. So that's a very powerful. Okay, so someone's asking in the direct chat. I won't use names, and they definitely should get points for this. They should submit for boards. Someone's raising the example of a pendulum, based on what I think writing here. Now that is a very powerful example, and in fact, I will even say that hopefully, Quark willing, you'll all be with me for Physics 204, and we will spend a lot of time talking about pendulums in 204. Like a pendulum is a very, very important piece of physics equipment and history and phenomenon. I'm not sure if it's 100% the best. I'm not totally sure what the person has in mind about why this relates to pendulum. But I think I do. Yes and no. Let me explain what this law is. I mean, the pendulum is a good illustration in a way of back and forth motion, but this is about back and forth pushes or pulls. So let me tell you what I mean. This law says if one object exerts a force on another object, that if object A exerts a force on object B, then object B exerts a force on object A of equal magnitude and opposite direction. In a way, the surprise part of this law might be the equal magnitude part. This is the law that is sometimes referred to as action and reaction. You may have heard of it that way, but it's not sufficient, honestly. It's not good enough to just say, oh, for every action, there's an equal and opposite reaction. That does not actually, first of all, it doesn't capture all of the nuances of this. And second of all, it actually makes us picture certain things that we shouldn't be picturing, according to this. What this thing is saying is, and you might want to even write this down to the side or something, what this thing is saying is, if I push you, you push me back with exactly the same magnitude of force. I mean, going back to Denny's now, in other words, okay, it is saying, and I don't care if I'm an animate object or not, it is saying, if this is a wall, if I push this wall, the wall pushes my hand back. And if I push this wall to the north with 100 newtons of force, the wall automatically pushes my hand back to the south with 100 newtons of force. Now and it's not about revenge. It's about reality. Let me be more clear. I wish I could do this I can't really do this on Zoom, but if I push the wall, can I do this? I'm on a stool, but yeah, okay. Here, so I'm going to push, but I'm going to push the table now, okay? I'm going to push toward you. That was the stupidest thing I've ever, okay, everything just went crashing. But if I push the table, okay, I'm going back right now. Yeah, firing a gun is a great example. Yes. Sorry. Did I say that? I didn't say the person's name. Firing a gun is a great example. Yes. And let me be very clear about this. No, like the kickback of firing a gun. Yes. And the reality is this is always happening whenever there's any force at all. If I push a table, the table pushes me back. If the chamber of a gun pushes forward a bullet, the bullet pushes the chamber of the gun back. Now note, here's the thing. Note, like if I push the table and I go back a heck of a lot faster than the table went forward. In fact, if the table's like a wall, if I push against a wall, you don't even see the table. I mean, you don't even see the wall move, but you do see me go careening back. So it can really look deceptive. It can look like forces come in opposite pairs, but it can look like the forces don't come in equal magnitude. It can look like I push the wall a little bit and then the wall pushes me a lot. I go flying or something like that. But what yes, good, John, yes. because what you're seeing is acceleration. That's right. If I push the wall and the wall pushes me, I will accelerate a lot because I have, that's very good, because I have very small mass compared to the wall. But the whole assumption is, I mean, if you're saying, oh, small m means big A, which is true, that's what John Ford is saying, that's the second law. If we're believing, oh yes, small m mass means big acceleration, what are we just tacitly assuming in our mind? We're assuming same F. We're assuming if you hold F constant, if M goes down, then A, when we say M and A are inversely proportional to each other, we mean that if you hold, in order to hold M constant, if you make M half as big, then you're going to make A twice as big, right? But that assumes that M is constant. And that's what's actually happening here. When I push the wall pushes me back the same push. It's just that now, in other words, the causes are the same in magnitude. Now, what effect those produce, according to the second law, is inversely proportional to mass. So you might see different effects. But if I push you, you push me back, or if I pull you in a tug of war and rope, or like the horse and cart problem of lab 4, if the horse is pulling the cart to the right, then the cart is pulling the horse to the left. And I mean, any horse, like if you know what I'm talking about, then you know what I'm talking about. But if you don't, any horse or any cart, if a horse is pulling a cart and they're like, you know, you see them walking down the road to the right. If the horse is pulling the cart to the right, then the cart is pulling the horse to the left and by the same amount. So if by the same amount, it's not losing, it's tying necessarily. So if the whole system is in fact accelerating to the right, as is the case with the example you're asked about, there's got to be some other explanation, something else going on, some kind of external forces on the horse and the cart that are different, because just what's happening between the horse and the cart has to be reciprocal. What I'm getting at with now, how does this help us at all? What this tells us is really what a force is. This tells us the nature of a force and how to identify it. Both in diagrams and in math. Let me just turn the page and I'm going to look in the chat in 1 second. Hold on. Yeah, okay. So what this says, and I'll give you a moment to pause to copy this down. Also, I'll look in the chat. This says Newton's third law really tells us what a force is and how to identify whether one is present or not, like in a given situation. Newton's, I'm just reading out loud in case my handwriting is. Newton's third law enables us to create two types of force diagrams. Two types, the system schema and the free body diagram. Like we need Newton's third law in order to create these diagrams. And why do we need the diagrams? Like people sweat over the diagrams and a lot of people sort of also skip over the diagrams. They think it's just like some silly thing that's getting in the way of problem solving. The diagrams are the crucial piece of problem solving. We all know in our hearts that what's hard about doing problems in math or physics or science usually is not the doing them. It's usually the starting them, right? The hard part most people say, I get what's going on in physics or in chemistry or whatever. I get what's going on when you do it, but I just don't know how to start the problem on my own, or I don't know how to set it up. I don't know which equation to use, people say. Well, first of all, from here on in, which equation to use? F net equals ma. Everything from here on in your life in physics is F net equals ma. Sum of the forces equals mass times acceleration. The question is where to go from there, how to set that up, what to plug into the left side. And the answer comes from these diagrams. The answer, honestly, the diagram is not just an exercise. The diagram tells us what is a force and what isn't. And that's what I'm going to show you in a minute, like with the system schema and so forth. But Newton's third law is what conceptually gets us into these diagrams. So we need the diagrams in order to know what to plug into Newton's second law, because that tells us what a force does. And I'm about to show you how to do the diagrams. One thing I just want to see. 1 second, sorry. Oh, yeah, okay. Tell me if you want, well, let me look in the chat. Well, you may need me to go back a page. I'm sorry, I've lost, I don't know where you were, but, oh yeah, that was good, John. Okay, so the chat is fine. So I'm going to assume that. So what this says now, and tell me if you want me to go back, but so the third law says, I push you, you push me back, always, like necessarily, like same magnitude. So what Newton's third law is saying is that a force is a symmetric interaction between two identifiable masses. It's saying force is interaction. A force is not a description. A force is not something that an object has. It's that force is not like energy or temperature or something. Like again, force is not a property. It's never correct to say the baseball has a big force. Like you hear people say that sometimes, but it's never correct. It doesn't mean anything. A baseball doesn't have a force. I don't have a force. Luke Skywalker maybe has a force, but I don't know what that means. What is the case is that I can exert a force on you. I can push you, or I can pull you, or I can pull the can of Coke toward me, or I can push the can of Coke away from me. A force is what one object does to another. It is an so it's, I think I get that, sorry. For a force to take place, an interaction has to take place. Action meaning like verb, like thing being done. And inter meaning between two objects. So a force is something that one object does to another. And by object, I mean mass, like identifiable, nameable, countable, discrete, locatable object, such as can of Coke or pen or string or planet Earth. But for there to be a force, there have to be two objects. And so when if we want to know, is there a force on that cannon that's flying, or is there a force on that sandwich, whatever it was, I keep forgetting. I don't know why I keep the dish rag or whatever. Is there a force on an object, on an inclined plane, on a table? If you want to know, you have to ask, well, is there another object interacting with my mass? If so, then there's a force acting on it. If there's two objects interacting with my mass, then there's two forces acting on it. For there to be a force, there has to be another object in interaction. And I'm going to say one more thing before I look at the chat. Here's where it gets even more concrete. If you're wanting to know whether two objects are interacting or not, with the exception of gravity, gravity is the one exception that's always there that's really weird. With the exception of gravity, for things to exert forces on other things, they have to touch. If I want to believe that something is exerting a force on the Coke can on my desk, something has to touch the Coke can. The one exception is gravity. Gravity is the name. And excuse me, gravity is not an exception to the interaction idea. It's an exception to the touching idea. For the Coke can to be falling down, for gravity to be pulling on it, there's this thing that has to be there called planet Earth, or the center of Earth, which is pulling on the Coke can. Now, somehow, planet Earth seems to be able to pull on all objects without touching them. It seems to be able to exert a force, an interaction, without physical contact. In the whole context of mechanics, gravity is the only force that does this. It's the only force that acts without touching. If it weren't for the fact that gravity is so obviously here all the time, if it weren't for the fact that we are so familiar with it in our daily lives, we wouldn't believe in it. It is an exception to the rule. And it's so mysterious, it's so strange that gravity does this, that for centuries and centuries, physicists thought very hard about it. They had to devote a whole separate set of thoughts to just how gravity works, because it's so bizarre that the Earth, and it turns out other objects, can exert a pull without even touching. But it does. We see that it does. So from here on in all of our diagrams, in all of our situations, if we're ever trying to identify what forces are acting, first and foremost, we always put Earth in. If we're drawing a system schema, we always draw a circle representing Earth, because Earth is always there and it's always pulling, and it's always pulling even without touching. And we'll never be wrong by putting it there. And if we don't put it there first, we might forget it, because after we write the Earth, then the only forces we ever write down from then on in, after we write Earth in a system schema or in a free body diagram, the only objects that we ever name as causing forces are objects that are touching our mass of interest. So it's all about touching, with the exception of gravity. Let me just look at the chat, and then I'm going to go on to the next page. Oh, great question. Wait. Now listen, I think my issue thing is funny, although I admit I'm not sure I totally get it, but I think it was a Luke Skywalker thing. Now, John Ford's thing is very, very important, very like valid. I'm saying there's only what we're in right now. This context is classical mechanics. This is mechanics. I'm not being sarcastic. I'm being serious. This context is mechanics. So in the context of mechanics, in the context of macroscopic observable motions, the only exception to the touch idea is gravity. But yes, you're right. Once we start looking microscopically into other areas, then things like electricity and magnetism come up. That is the focus of the next course of Physics 204. Like totally legitimate point. I mean, John's right. Somehow protons and electrons seem to be able to pull each other without touching. And somehow that ends up making this whole phenomenon called magnetism, which seems to be able to happen without touching. That's totally a real thing. That's also, and the weirdest thing is that those forces mathematically work exactly the way gravity does mathematically. There's something about all of these actions at a distance that makes them all very mathematically common. And it's a huge focus of Physics 204. So totally legitimate point. But I'm saying right now in this context of Newtonian classical mechanics, of macroscopic phenomena, gravity is the only. So in other words, those things would never be on your final exam or anything like that. Gravity is the only force that acts without touching in this context, and the only one that like Newton did anything with. But totally fair point. And and feel free to say gotcha or whatever if you do, and you'll get points for closing the conversation. But okay, so let me go to the next. Oh, so one quick thing. What I'm trying to say about forces in Newton's third law is that forces are interactions between pairs of objects, and they're necessarily symmetric. They're necessarily symmetric, they're symmetric. It sounds surprising in a way that the amount that I push the wall is the exact same amount that the wall pushes me, but it's not really a surprise when you just think about it as a semantic point. Like guess what, guys? I married my wife on October 20th, 2000 or whatever. And guess what? My wife married me on October 20th as well. Is that a weird coincidence or what? Can you believe it? Like my wedding anniversary date is the same as my wife's. Can you believe that? Yes, of course you can believe it, right? Because that's idiotic that I would even say that, because duh, right? Like duh, of course, when I married my wife, she married me, because that's what marriage is, right? Or wedding or whatever. Like obviously I can't be married to my wife unless she's married to me. And I can say I married her. She could say she married me, but that's just the way we're saying it. That's just our frame of reference. The point is that there's a mutual symmetric interaction between the two of us called marriage, right? Not to get all weird and romantic, but that's, yes, that's very funny, right? But that's what we're saying about forces now. We're saying, look, forces, you can look at it as the earth pulling down on a brick, or you can look at it as a brick pulling up on the earth, but that's just a question of how you look at it. What's happening is a mutual symmetric interaction between two objects. A pull is occurring, and we call that pull a force. So if you think about it, this should sound very familiar. It's kind of like what I was yelling and screaming about velocity like weeks ago, months ago, days ago. Velocity, right? Like whether the earth goes past the sun or the sun goes past the earth is just a matter of frame of reference, just a matter of the way you look at it. But both frames of reference are equally correct. That's Galileo's principle of relativity. Velocity is a relation between two objects, not a property. We're now extending that even further to say force is like that as well. Force is an interaction between two objects. It's not a property, one, and it's symmetric. It doesn't go in one direction without going in the other. This is just yet another form of the same idea, just pushing forward into more advanced applications. So Newton's third law of motion is in effect the sixth form of Galileo's principle of relativity. I don't know if that makes it easier or harder to assimilate, but it's the same, really the same kernel idea. Now, I know I only have 10 minutes, but I got to apply this to diagrams. Yeah, sorry. I know. Thank you, Mark. I totally caught that. What year did we get married? We got married just before I get in trouble with doing that. We got married in, oh my God, 2012. Okay. Thank you for reminding me. Okay. Thank you. Okay. So now what I'm going to do is I want to, in the 9 minutes that we have, I want to apply all this to like drawing system schemas and free body diagrams. We'll probably only get to the schemas today. But again, the purpose of the diagrams, the diagrams seem all just like, oh no. Oh, yes, that's true. Thank you. Well, we'll need a YouTube on. Yeah, right. Thank you for noticing. Yes, you'll be the first to. Anyway, actually, when we need to renew our vows at year 20, I think Althea is going to be the one too, because I think she's going to be a priestess of the highest order by that point. And I think and she'll, yes. Anyway, okay, October. I'm just okay. Clapping at myself. All right, what I want to quickly show you in 8 or 9 minutes is sort of how to draw the diagrams. And the point of the diagrams, again, is the diagrams force you to know what exactly is a force and what is not, and therefore enables you to know what to plug into the left side of F net equals MA in order to calculate A. That's, all of this is actually to set up the math for F net equals MA. Okay, why do I actually believe that strangely? Okay, so, and what I'm going to do right now, especially because now we only have 8 minutes, is I'm going to jump straight to the to the hardest example, or one of the hardest examples, because if we can do, like, because you all have already been wrestling with examples in lab 4, but I think if I can go straight to a super hard example, I think then you'll know everything. So, and you may or may not ever get to see this in lab 5, but just to pick. Oh my God. Okay. So let's picture a mass, like a block, on a rough inclined plane. Like, this is like putting together as many different factors as I can at once so we can get all the issues out on the table. Like, imagine that we have like a slide, like a ramp. So like a tabletop, but it's like bent at an angle. And imagine that the tabletop is rough. So I have these jagged like lines, indicating that. And I have the Greek symbol mu, which is used to indicate a roughness factor, what they call a coefficient of friction. Mu could be a number anywhere from 0 to 0.99999. So it's like the higher the number, the rougher the material, whatever. So I'm saying we have this rough slide. We have an object of mass M on the slide. The slide is angled at angle theta, let's say. And let's say that with 7 minutes left, yeah, the rougher, you're correct. The rougher the surface, the higher the mu, if that's what you're saying. Absolutely correct. Yes. Oh. Wait. Well, yeah, basically that's right. I mean, the way the molecules are arranged is ultimately what determines how rough the surface is. Yeah. So now let's picture, just to make this sort of as hard and complete as possible, let's even picture that we've got some mass that's on its way up a slide because someone like pushed it like 5 minutes ago. Someone gave it an initial velocity from the bottom, and like now it's on its way up. And now we take one moment somewhere during its ascent to analyze. It's like, so we take some moment in time, some point in space, to analyze what are all the forces acting on this object while it's going up a rough inclined plane. Okay, we got 6 minutes. And again, if you can follow this, you could follow any example. Like, this is about as elaborate as examples get. So I want to first draw a system schema. In a system schema, the purpose is to even figure out what all the forces are, just to identify them. And the way we do that in a system schema is we figure out what all the forces are simply by asking ourselves, what are all the other objects in the world that are directly interacting with this one meaning the mass of our interest, the block that's on the inclined plane. Okay, so when we draw a system schema, the purpose is to identify every force, everything that's actually force, and to exclude anything which might seem like a force but isn't. And the way we do this is we identify the particular objects that are interacting directly with our mass. In the system schema, direction does not matter at all. We don't care about direction. We just care about identifying the actual forces themselves. So the way we do this, so in order to do this, we draw a dotted circle to represent our mass of interest, the block in this case. We draw a dotted circle, M. And then for every object that's interacting with this object of focus, we draw a solid circle. And we connect all the circles with lines. Now, and here's the key thing. I know we only have 4 minutes. So here's the thing I want to say that probably wasn't clear when you were in lab, that might clarify things right now. You draw a solid circle for every object interacting with our object, and that includes planet Earth. I'll show you in a second. And you follow this rule, and then you connect all the circles with lines. And in order to draw the lines, you follow a rule that I call the one touch, one line rule. One touch, one line. Just know that there's always precisely exactly two important exceptions to this one touch, one line rule. If you know the rule and you know the exceptions, you'll get the whole thing. The rule is for everything that's touching, you get a line. For every one touch, you get one line. The two exceptions, and the two exceptions are what you should probably draw first, before you get confused, are, and I'm going to show you this, and I know we have 4 minutes. I'm going to show you my answer on the next page. But the two exceptions to the one, so again, it's one line, one touch. You're drawing one line for every touch that you observe. And the whole importance of this, again, is the only things that are doing anything, the only thing that count as forces are things that are touching our object. But the two exceptions are, number one, planet Earth is always there and is always pulling on our object, whatever our object is. There's always planet Earth, and planet Earth always gets a line because it's always pulling on our object, even though planet Earth is not touching. Gravity is just a big exception that way. Newton didn't understand why that was happening or how. It took us all the way to Einstein to understand how, in a way, how non-touch forces like gravity work, but it's clearly happening. So here's my, so we have a dotted line, a dotted circle to represent our mass. Again, this is a system schema of some object that's going up an incline, a rough inclined plane on an angle. Notice directions have nothing to do with anything in this picture. I'm just drawing the objects that are interacting with my mass of interest. So first of all, off to the left, I have this solid circle that says CE. CE stands for center of Earth. You could write PE like planet Earth if you want, or you could write EE like entire Earth. I'm just somehow trying to connote that it's Earth as in the planet, as in the gravitational body, like not as in ground or dirt or something like that. So I've got the Earth wherever I want it with one line connecting to the mass. I always have a CE. I always has a line connecting to the mass because objects always have weight. They're always being pulled by Earth. Then I, having drawn that, then I look at the object and I'm like, now that I put in Earth, now that I put in that exception number one, now I look to see, is anything touching my object? Anything and everything that's touching my object gets a circle. Well, the one thing that's touching my object is the plane that it's on, the slide. Right? And if this were one of the examples from lab 4, like if this were a tabletop, you'd put tabletop or whatever you want to call it, or desk or whatever, like that would get a circle because the desk is touching the object. The thing is, here's the other exception now. But by the way, notice those are the only two things interacting. Even in this complicated example that has friction and has an angle and all that, there's only two things interacting with my object: planet Earth, because it always is, and then the table or the plane, because the plane is touching the object. But notice now, and this is where we're going to end today. If the table were simply like some string or something just pulling on our object, as is the case in some of those examples from lab 4, if it weren't a table, if it were like a string pulling or something, then I would just draw one line for that, just one line. But because one line, one touch, for every touch, you draw one line. But the other exception here is that whenever you have, and this is what it says here in red, if you ever have two surfaces pushing on each other, kind of because of what John Ford said before, when you have two surfaces pushing on each other like this, the truth is microscopically, rough surfaces have lots of bumps and ridges. And I know it's 4:20, I'm just finishing the sentence and then we're done, and then have a happy Thanksgiving. But rough surfaces, if you look at them microscopically, are ridgy, they're bumpy, they're clawy. So when you push two rough surfaces together, they actually hook into each other and grab onto each other. And by pushing against each other like this, they also make it hard for them to slide or rub along each other like that. In other words, whenever two surfaces push perpendicularly against each other, they also slide and rub against each other. This perpendicular push we call normal, simply because normal in math means perpendicular. So whenever two surfaces push in any way, when you have two rough surfaces pushing, there's a normal component of the push. That's the push against that is happening automatically, but that will always produce a push along the parallel to the plane of contact, parallel to the surfaces themselves, a sliding rubbing force that we call friction. In other words, anytime two rough surfaces push against each other, they actually interact in two ways. One way is called the normal force. The other way is called friction. It's really just two components, two axes, two directions of one big phenomenon. And that phenomenon is rough surfaces pushing. So whenever two surfaces push, we make two lines for that in the system schema, because it's really two force effects that occur. Whenever the Earth pulls on an object at all, we put one line because there's a force of gravity. And then from then on, anything else that's touching the object gets one line. That's it. In this case, there's nothing else affecting the object. There's nothing else going on. So that's the whole system schema. There's one more page of notes that you can look at if you're interested. One more page of notes that tells how to do free body diagrams. If you're interested, you can look at that on your own time. But I'm going to end there because I have the other class coming in, because you have to have a very nice Thanksgiving, and I will get your exams back. Yes, happy Thanksgiving. You guys are great. I will miss you. I cork you, whatever. That's weird. But yes, have a great Thanksgiving. Thank you for your attention. Yes, have a great, and I'm turning off the recording, but have a great Thanksgiving. Quark bless America. Yes, thank you. No, I'll try not to make days off. I'll try to just finish your exams really, but you too, and I'm stopping the recording.